Good day. So let's have another example for the shear and moment diagrams for beams. For example, we have this cantilever beam AB with a span of 12 feet. So it carries a concentrated load of 1,000 pounds that is upward at point A. And a varying load with a magnitude of 0 at point A to 360 pounds per foot at point B. To start our solution, let us first compute for the support reactions. So we have at B, let's say we have R sub B that is assumed to be upward. And since it is a fixed support, we have a moment at B, I assume to be, let's say, clockwise. We don't have a horizontal force. Okay, for the varying load, let us compute for the single equivalent force. Let's say this is W. So how do we compute for that W? That is basically equal to the area of the triangular loading. We have that is 1/2, the base is, this is 12 feet. Then we have 360 pounds per foot. We are to cancel the unit feet. Obviously, the remaining unit will be equal to, pounds. So that is, we have 1/2, that is 0.5 of 12, multiplied by 360. And this is equal to 2,160 pounds. So we have 2,160 pounds. Okay, so to compute for R sub B, we do the summation of forces, vertical equal to 0, assuming upward forces to be positive. So we have the 1,000 pounds at A plus the reaction at B, minus the weight, that is 2,160 pounds, equal to 0. So we'll be having the reaction at B is obviously we have the difference of the two, that is equal to 1,160 pounds. This will be our reaction at B, and it is upward. So we have R sub B is 1,160 pounds. Then for the moment of B, we do the summation of moments at point B equal to 0, assuming clockwise moments to be positive. Okay, so since we have a varying load, this single equivalent force is assumed to be acting on the centroid of this triangular area. So from point B, it is assumed to be acting at a distance of 1/3 of the span, 1/3 of 12. From point A, it is 2/3 of 12. Okay, so we are now doing the summation moment at B. So what are the clockwise moments? That is, assume clockwise moment is the moment reaction at B, plus we have the 1,000, multiplied by 12 feet, then minus, this is 2,160, at a distance of, this is 1/3 of 12 feet. And this is now equal to 0. So computing for the moment at B, that is, we have 1,000, this is multiplied by 12, minus, we have that is 2,160, this is multiplied by 3, 1/3, or this is multiplied by 12 over 3, the 1/3 of 12. That is 3,360, and it is positive. If we transpose this one, so it will give us a negative 3,360 pounds foot. See if we have to check that, negative 3,360. So we arrive with a negative sign, which means our assumed direction for the moment of B is wrong. It is not clockwise. The moment reaction at B should be counterclockwise. Since we arrive with a negative sign. So let's say we have the moment at B is equal to 3,360 pounds foot. So again, on our moment equation, we arrive with a negative sign, and we assume that moment at B is clockwise. So which means the correct direction of the moment at B should be counter. It is a counterclockwise moment. Okay. Okay, so I think we are now ready to draw our detailed shear and moment diagram. So starting with the shear diagram, okay, we have at point A, let's say starting from 0, starting on the left end, okay, we have an upward force of 1,000 pounds. So that is from 0, okay, we go up, let's say to a magnitude of 1,000 pounds. Okay, so kindly observe this one. Our loading is a first degree load. So we have N is equal to first degree. That is a varying load. Okay, so let us just add some key points. If we have our load diagram to be a first degree, so let's say the degree is first degree. As we go down on our diagrams, if we proceed to our shear diagram, we increase the degree by 1 degree. So the degree of the shear diagram should be second degree, which means it is a curve. Then again, as we go down, if we proceed to the moment diagram, we increase the degree by 1 degree. So the degree of the moment diagram should be third degree. Starting at second degree for the shear diagram, that is a second degree, that is a curve or that is a parabola. But we don't know yet if that is a parabola that opens upwards or a parabola that opens downwards. So, to help us decide what will be the opening of the curve, take note that the slope of the load diagram, or that is the slope of the shear diagram, is basically equal to the magnitude of the load. If we have a downward load, which means we have a negative slope for the shear diagram. If we have an upward force or upward load, which means we have a positive slope for the shear diagram. Okay, so we have, if we are now to do the summation, that is basically 1,000 minus 2,160. Okay, we have these 2 points as our reference points. So we have A and B, okay, the 2 ends of the beam. Okay, what is the magnitude of the varying load at point A? So we have the magnitude of the varying load at point A is 0. This corresponds to a 0 slope on our shear diagram. What is the magnitude of the varying load at point B? That is equal to 360, and it is downward, which corresponds to a negative slope. Okay, at point A, what is the appearance of a line with a 0 slope? So appearance of a line with a 0 slope is basically a horizontal line. Okay, let's say that is the tangent line at point A. Then at point B, we have a 360 downward. We assume that to be a negative slope. The appearance of a line with a negative slope is downward to the right. So let's say this is point B. We are just to connect these 2 points with a curve. So using these 2 lines as our tangent lines. So if these 2 lines are the tangent lines, the curve connecting these 2 points should be a curve that opens downwards. So this is it should be a curve that opens downward for the shear diagram for span AB. So we do the summation. That is, we have 1,000 pounds minus the downward single equivalent force of the varying load. That is the 2,160. So we have 1,000 minus 2,160 will give us a negative 1,160. And a curve that opens downwards. So this is a curve that opens downward. Okay, with a magnitude of, the magnitude of the remaining shear at B will be equal to negative 1,160. Okay, but at point B, we have an upward reaction of 1,160 pounds. So we do the summation. Negative 1,160 plus 1,160, that will give us 0 for equilibrium. So this will be our shear diagram. Okay, so how do we draw our next diagram? That is we have the moment diagram. For our moment diagram, we need first to determine this location of zero shear. In our shear diagram, we have this point. We have the shear is equal to 0. So to determine this point, all we have to do is I cut the beam. I then cut and expose. Then we do our mechanics. So let's say we assume this distance from point A. Assuming this distance from point A to be x. So we cut that beam at a distance of x on the location of, we have this as this point with the magnitude of shear equal to 0. So let's say this point of 0 shear, we name this point as, let's say, point C. So at point C, the magnitude of the shear is equal to 0. But if we are to proceed on our varying load, we don't know the magnitude of this varying load at a distance x. So we do the ratio and proportion of our similar triangles. Our bigger triangle is we have the 360 pounds per foot, corresponds to a length of the beam 12 feet. Then this is equal to the magnitude of omega corresponds to a distance of x, which is the cut distance. So if we are to compute for the equivalent of our varying load at that point, that is equal to 360 over 12. That is equal to 30, I think. What is 360 divided by 12? That is 30. So that is the same as 30 of x. This is the same as the pounds per foot. So we have this value equal to 30 of x pounds per foot. How do we compute for the value of x? The location of the 0 shear from point A. So all we have to do is what will be the equivalent single force equivalent of this varying load. So let's say this is the W sub 1 this time. So how do we compute for the equivalent of W sub 1? That is basically equal to the area of this triangular loading. That is 1/2. What is our base? That is x. What is the height? The height is, we have 30 times x. So the equivalent of W sub 1 is basically equal to 15x squared. So we have W sub 1 is that is 15. We have 15 of x squared. So since we have a shear equal to 0, all we have to do now is do the summation of forces vertical equal to 0, upward forces to be positive. So what are the upward forces? We have only 1,000, that is the 1,000 at point A, minus our downward load, that is the single equivalent force of the varying load for a distance x. We have that as 15x squared, and this is equal to 0, since we have, again, a 0 shear. Okay, what will be the value of x? That will be, we have that as 1,000. This is divided by 15. Then we take the square root. So that's 8.1649, or we can have it as 8.165 feet. Alright, so we are able to determine the location of this 0 shear from point A, that is point C. We have the value of x is equal to 8.165 feet. How do we compute for the moment at that point, at point C? So again, how do we compute for the moment using the area method? Again, we have area, or the moment. The magnitude of the moment can be computed as the area of the shear diagram. Alright, so all you have to do now is, starting at A, point A is a free end, so obviously the moment at A is equal to 0. So we are now to compute for the moment at C. We have the moment at C. This is the moment at C is basically equal to the moment at A plus we need the area of the shear diagram for the span or for the segment. This is from A to C. So the free end is point A. Then the location of the zero shears, that is point C. So what shape is this one? So this is a second degree curve, and it is a parabola. We have n is equal to, this is second degree, since our load diagram is first degree. Okay, how do we compute for the area of a parabola? Okay, the area of a parabola is equal to, this is 2 over 3 of the base times the height. Computing now for the moment at C. This is the moment at C is equal to, our moment at A is equal to 0. This is equal to 2 over 3. So what is the area of our parabola? So we have, let's say, a base of 1,000, that is 1,000 pounds, multiplied by its height or its length. That is 8.165 feet. This is 8.165 feet. This will be the equivalent of the moment at C. But since that is also the location of the zero shear, possible that this is our maximum moment, since we have that point as zero shear. Okay, computing for that value, so that is, we have 2 over 3 of 1,000. This is multiplied by, this is 8.165. Okay, we have that value as 5,443.333 and so on. So it's 5,443.333. This is pounds foot. Okay, this will be our, I think, the maximum moment. Okay, how do we draw the moment diagram? So all we have to do is observe. Observe the magnitude of the shear on our shear diagram. Okay, so since our shear diagram is second degree, our moment diagram should be third degree. Let us observe our reference points. We have point A and point C. What is the magnitude of the shear at point A? That is, we have positive 1,000. The shear at point C is obviously we have a 0. So what is the appearance of a line segment with a positive slope? So the appearance of a line with a positive slope, that is a line drawn. It should be a line upward to the right, since it is a positive slope. Then at point C, we have the shear is equal to 0. That is an equivalent of a zero slope on our moment diagram. So a line with a zero slope is a horizontal line. So let's say our first point is point A and second point is point C. We connect these 2 points with a curve. So it should be a curve that opens downward. Okay? A positive slope and a negative slope. Okay, so starting at A, that is a zero moment, to point C. So it should be a curve that opens downward. Alright, so this is our maximum moment, I think. With a magnitude of 5,443.333 pounds foot. Okay? So how do we compute for this area, the negative area on our shear diagram? Okay, how do we compute for this one? We may consider a larger, let's say a larger spandrel. Okay, now so how do we compute for the moment at B, and how do we compute for this negative area on our shear diagram if we are to use the area method? So we have this segment from point C to point B. Let's have another figure for this one, for our shear diagram. So we have this, our shear diagram. So on the left end, this is point A. So we have point C. We are able to compute that as 8.165. 12 minus 8.165 is 3.835. We are looking for the area of this shear diagram, the negative area. And this is point B. Okay, we may consider the larger spandrel. since this is the part of a spandrel. Okay, the appearance of our larger spandrel will be this one. I'm using the green pen. This is our spandrel. Okay, how do we compute for the area of a spandrel? The general formula for the area of a spandrel is equal to, this is 1 over the degree of the curve plus 1 multiplied by the base times the height. But we are not, we don't need the total area of the spandrel. We just need this area which is part of this spandrel. Okay, we may divide our areas into 3. So again, we are only computing for the area of a spandrel if we have one of its side is a tangent line. This is a tangent line. For a reason, that's the slope at A, the slope of the shear diagram at A is equal to 0. So the slope at this point, the slope of the tangent line of this point is equal to 0. So we are sure that this horizontal line is a tangent line. Okay, so again, why is it that slope is equal to 0? The magnitude of the varying load at point A is 0. So we are dividing the area of the spandrel into, let's say, 3 areas. So we have this one is a smaller spandrel. This is a smaller spandrel. Let's say this is area 1. This remaining area is a rectangle. Let's say this is area 2. Then we have this height is the same as 1,000. How do we compute for this? The area of the shear diagram for the span. This is for the span CB. That is basically we have, if we are to write our equation, the area of the shear diagram for span CB is basically equal to the area of the spandrel. What is our bigger spandrel? Our bigger spandrel, we have this dimension. Let's say it's a base. What will be this dimension? If it is 1,000 upwards and we have negative 1,160 below, so we add that. We take the absolute value. That is the same as 2,160. And its corresponding length is the length of the beam. The length of this bigger spandrel is the length of the beam, which is the same as 12 feet. How do we compute for the area of the shear diagram for the segment CB? That is the area of this spandrel, or our bigger spandrel, that is 1. That is 1 over the degree of the curve. Take note, it is a second degree curve. Our N is a second degree curve for our shear diagram. So it's 1 over 2 plus 1. Our base will be equal to 2,160 for a length of 12 feet. Minus, we are to subtract area 1. That is a small spandrel. That is the same as 1 over n. The degree of the curve is 2 plus 1. Our base is, this is 1,000 for the smaller spandrel for area 1. That is 1,000 multiplied by its corresponding length. Its corresponding length is the 8 point. This is 8.165. Then minus this rectangular area. This is area 2. What is area 2? This is area of a rectangle with a height of 1,000 and its horizontal width that is equal to 3.835 feet. So we are now computing for the area of the shear diagram for segment CB. And this is equal to, we have, that is the same as 1/3. It's 1/3 of 2,160 this is multiplied by 12, then minus, this is 1 over 3 of 1,000. This is 1,000 multiplied by 8.165. Then minus the area of the rectangle, that is equal to 1,000. Is 1,000 by 3.835. So we have this value. This is equal to 2,083. 2,083.333. That is equal to 2,083.333. Since this is area of a shear, which is equal to magnitude of a moment, that is equal to, this is in terms of pounds of foot. But to be precise, this is a negative area. This is a negative area. So we assume this to be supposedly a negative area. Now we can now compute for our moment, the moment at B. So the moment at B, computing for the moment at B, that is our moment at C, our initial point, plus the area of the shear diagram for the segment CB. What was the magnitude of the moment at B? We have it as 5,443.333. So again, this is a negative area, so it should be subtracted, or it should be a negative area. So from our previous computation for area of the shear diagram for segment BC. So we have the moment at C. This is the moment at C. We have 5,443.333 plus the area of the shear diagram for segment BC is a negative area. That's negative 2,083.333. We compute for that value. That is equal to 5,443.333 minus 2,083. It's 2,083.333. So we have that moment as positive 3,360. It will be the moment at B will be equal to positive 3,360. This is pounds of foot. So if we are to draw that or put this detail on our moment diagram, so from 5,443.333, so we go down to a value of 3,360. By the way, what will be the equivalent of or the appearance of our graph? So we have at point C, we have the magnitude of shear is equal to 0. At point B, the magnitude of the shear is negative 1,160. If we are to check on our shear diagram. So at C, 0 shear. At B, negative 1,160. What will be the appearance of the graph? So again, we have B is equal to 0. That is a 0 slope. So that it corresponds to a horizontal tangent line. At B, we have a negative slope, that is a tangent line drawn downward to the right. If we are to connect these 2 points or these 2 tangent lines using a curve, it should be a curve that opens downward. And it should be a 3rd degree. So from 5,543, we go down and the curve should opens downward. We go down to a magnitude of 3,000. This is 3,360 pounds-foot. But at point B, we have a moment that is equal to 3,360 pounds-foot. It is counterclockwise, and it is assumed to be negative. So if we are to do the summation, that will give us a value of 0 for equilibrium. That is, but the moment at B is 3,360 pounds-foot. So this will be our moment diagram. Okay, the moment at B is 3,000. This is equal to 3,360 pounds of foot. And the degree of our moment diagram, since our shear diagram is second degree, the moment diagram should be a third degree curve. Okay, so this will be our moment diagram. And this will be our solution for this example.